It's our last session of the day. We have two more talks. So first, we're going to start with Aliza Siddiqui, and she's going to be talking about some work she's been doing with John Dowling. She's currently an undergraduate at LSU, and so it'll be interesting. We're going to learn about quantum networks, how to assess them, and how well they're doing, figures of merit thereof, and take the stage.
Good morning. My name is Aliza Siddiqui, and today I will be discussing the robustness of various quantum networks. Okay. So what exactly is a quantum network? A quantum network is a system used to distribute entanglement between members across large distances. And the ultimate goal is to have a quantum internet, which is a global interconnected network of quantum networks which can perform many quantum computing tasks, such as quantum synchronization, quantum teleportation, and quantum key distribution, and amongst many others. But the most anticipated use of the quantum internet so far is quantum encryption, or quantum cryptography. Believe it or not, our quantum internet today is protected by a very long division problem that mathematicians are so sure that no one can solve. And they are right. Classical computers cannot solve the public encryption system. They would give an overflow. But what happens if we add a quantum computer to the mix? They're being built right now as we speak. Quantum computers can solve these problems more efficiently than classical computers can. They can break our public encryption system. Our internet is not safe. So what do we need now? We need a quantum encryption system that even a quantum computer cannot crack. And in order to do that, we need to realize the quantum internet. So there are some challenges in realizing the quantum internet. For one, a qubit is so fragile. It is so easy to disturb its state. It just messes up with the slightest bit of noise. And also, for fiber optic cables, they are so lossy. Their physical properties themselves can absorb the qubit to where it cannot even reach where it wants to go. And a possible solution to that would be the quantum repeaters. And what the repeaters do is that they perform entanglement swapping and entanglement purification, which perfectly entangles two qubits if they are not perfectly entangled. But there's the rub. Entanglement purification requires quantum memories. And right now, quantum memories are very hard to obtain. And even if they were obtainable, they would be very expensive. So, okay, despite all these hindrances, our ultimate goal is to have a robust network architecture that can function despite node and link failures, and that we can implement with current or near-term technology. So with my work, I was determining the critical bond probability of different network lattices, and in my case, I studied finite lattices, while prior work had studied infinite lattices for calculation simplifications. And I basically compared my critical bond probability results to their critical bond probability results. And I also studied a new network architecture called the quantum network tree, in which several parties try to communicate with a target party. And I tested its robustness by node deletion. So I will get to that later. So a quantum network can be realized using photons sent along a fiber optic cable. Prior work used a network with source stations in the middle of each edge. And what these source stations would do is that they would generate and fire dual rail entangled photonic qubits. So these qubits, they're in the same state. They make a pact with each other. They're like, hey, if we are measured, this is the state that we're going to display. They shake on it, and then they are sent off along opposite ends of the optic cable. One here, one here. And when they get to the measurement terminals, which are indicated in gray, these measurement terminals perform a Bell measurement on whatever qubits arrive in these terminals. And the Bell measurement does two things. First, it releases these qubits from the prior entanglement that they had with their partners, and entangles whatever in these measurement terminals themselves. And second, these terminals globally announce the results of the Bell measurement along with a label identifying which terminal the results came from. So let's say I have two companies, company X and company Y, and they're different branches. So if one branch was trying to communicate with another branch, they could use these globally announced results to recover the original quantum state and ultimately figure out which branch they are communicating with. So all of this is happening simultaneously. These source stations are shooting out these photons, and all this is causing entanglement swapping. So this measurement terminal is shooting out photons, this is shooting out photons, and this is creating a path between two parties that are trying to communicate with each other, a quantum channel, so to speak. And so this was very similar to bond percolation theory, because right now this is very probabilistic. There's no guarantee that the qubit will even arrive at the measurement terminals. And this matched with bond percolation theory. So with probability P, the qubit arrived at the measurement terminals, and with probability 1 minus P, it didn't. So what is percolation theory? Percolation theory basically deals with numbers and properties of clusters formed when sites are occupied with probability P. So specifically, bond percolation theory deals with entanglement probability. So with probability P, entanglement successfully exchanged. With probability 1 minus P, it is not. And site percolation theory considers the individual nodes. What happens if the node malfunctions? And what happens if someone starts to hack these nodes and just they malfunction, disappear from the network? Okay, so an important part of bond percolation theory is the critical bond probability. And what it is a threshold. And above this probability threshold, a large network cluster starts to exist. Okay. So the first part of my project was computationally calculating the critical bond probability for finite graphs. So I studied 3 different lattices, the hexagonal lattice, the square lattice, and the triangular lattice. And my program was in Python. I created a program in Python which created a graph that had edges with probability P. And for each edge, with a random number generator, I generate a random number between 0 and 1 for each edge. And if that number was greater than the edge probability, then entanglement was successfully exchanged. If not, it wasn't successfully exchanged. And I ran this for a large number of time steps to figure out a critical probability. And as you can see, the jump in this graph at this specific probability indicates that this is a percolation threshold. And above this threshold, you can see that the values are very close together and start to show a horizontal asymptotic behavior. This shows that above this threshold, a large network cluster starts to exist. This average cluster ratio is basically the ratio between the links in the largest cluster in the network over the total amount of links in the network. That's how it's calculated. So
Can you explain how did you choose the jump? Because you have at least 2 more jumps over there.
Yeah. Okay. Because this graph is basically extended out, but when we were looking at it sharply, there was a sharp jump here. And I also looked at when the values get more precise. So you can see that around here they start to get more precise. So this is like the probability that that a large number cluster starts to exist. Yes.
But with this, when normally you define the jump where the probability is 0.5.
Where?
Normally, this is what you do when you use a percolation theory or similar theories to find the critical probability. You just, you have 0 and 1, so the transition is when the curve cross half. I mean, that's normally the most common criterion used. Because those jumps are noise. Most probably those jumps are not physical. At least you have a model that predicts jumps on that transition.
But we were doing this with no noise. This was like
It doesn't matter, I mean, that jump is, I don't think it's real, at least you have a reason to have a jump,
Are you saying you want the vertical line shifted left a little bit?
yes.
Okay.
Like where it has that exponential kick
At
up? Or
half, I mean, you don't know, it's the transition normally, but.
Yeah, usually the transition is
fast.
like at some kind of inflection point in the curve. So I'm not sure if it necessarily has to be the case that it's at, and the average cluster size is like 0.5. I'm not sure if it has to be that. Usually these things depend on the particular lattice. But in this case it is, yes, I mean there's going to be statistical noise, which is the noise that you're talking about. Yes.
But I mean, I might just be reading into this, but it looks like she's defining it for where you start to see that asymptotic behavior take place. And like each point is getting closer to the next point, right?
Yeah.
Okay.
Okay, right. So over here, this value right here, this was what prior work had calculated with infinite lattices, the critical probability. And this is what I calculated with finite graphs. So as you can see, I got pretty close. I replicated the results pretty close. And okay. So this was particularly the good region. And why do I call this a good region? Because we want this region to be as big as possible. We want this critical bond probability to be small. The smaller it is, the more entanglement is possible. The more entanglement can happen and more nodes can be connected. As a result, a large average cluster can start to exist. So you can see the hexagonal lattice didn't do so well. It has a very large. Yes?
Should the values for the infinite and finite case be the same?
Yeah, around the same, yes. Yeah. Where was I? What was I saying?
Exactly.
Yeah, okay, yeah, the hexagonal lattice didn't do so
Aliza,
well.
is that well known that the infinite and the finite graph should have a close critical probability? I mean, that's not the case
The
for
finite
phase
will approach, it
transition.
will approach, as you increase the size.
What
it will
was
not
the
be-
size of the lattice that you
As
used
the
in your
size increases,
experiment?
it will approach, but it need not
Like
be
five.
exactly the same for finite.
500. No,
500.
500 nodes again.
Okay.
Okay.
But with the power of the size, with the small power of the size.
I'm sorry, so, yeah, I mean, as the size
Okay, so the
increases, it will
hexagonal
approach
lattice-
the true.
It didn't do so well. The critical probability was very large. And when you look at the square lattice, the critical bond probability is a little bit smaller, as you can see in and out of all three lattices, the triangle lattice had the lowest critical bond probability, which meant that it could generate a lot more entanglement. So basically, this proved that the triangle lattice is the most robust out of all three. I proved that from prior work that the triangle lattice was the most robust. Okay, so this was just bond percolation theory, right? I was just testing the edges. But what if I were to add in an additional factor of site percolation theory? What if I were to test node deletion? So in order to simulate this, with some probability p, the node would malfunction. And with some probability 1 minus p, the node would re-enter the network and start functioning again. And after adding in this additional factor, I got this for the hexagonal lattice. Now again, the hexagonal lattice didn't do so well. Look, under the contour, there's not a lot of graph here. This shows that the hexagonal lattice cannot handle a large site deletion percentage, and a large average cluster starts to exist only after a large bond probability. But now, when you compare the square and triangular lattice, you can see that the triangular lattice has a lot more graph under its contour. So I had discovered that the triangular and square lattice can achieve a criticality up to 30% site deletion, while the hexagonal lattice could only do so up to 25%, when the number of sites in the largest cluster is 71% of all sites. a lot more graph under this contour for the triangular lattice. The triangular lattice could handle a large site deletion percentage with a lower bond probability, therefore having a larger average cluster ratio. So even when simultaneously considering bond and site percolation theory together, the triangular lattice turned out to be the most robust one out of all three.
Does site deletion just mean that you like remove a
Remove
node?
nodes.
Okay.
Yeah. So these are other network architectures that we could have used. So I did bipartite entanglement between two nodes. But there could also be tripartite entanglement between 3 nodes, or four-partite entanglement between 4 nodes. And you can basically use these for cases like quantum sensing, or if you want to do quantum key distribution between multiple members. But this could be used for fissure work, basically. So that's all nice and all. We have 2 nodes communicating, just one node communicating with another node across a certain distance. But what if I were to change that? What if I wanted several members communicating with a target member across a large distance? And that is known as the quantum network tree. Now this topology consisted of 64 nodes at the bottom and 1 target node at the top, with around 2,015 middle terminals. So these terminals are just like measurement terminals with entanglement swapping happening in each of these terminals. So I want to test site percolation theory, aka node deletion, on this topology in order to test its robustness, or how strong it was with node failure. So I discovered that after deleting 2% of the sites in the middle, at least one node, one of the bottom nodes, would lose communication with the top. It would not have any sort of pathway to get to the top. Now this doesn't necessarily have to happen with this node. If I randomly delete 2% of these middle nodes, it is guaranteed that at least one of these 64 nodes will lose communication with the top. It would not have a pathway. And then I also discovered that I have to delete at least 50% of the middle nodes for all of these bottom nodes to lose communication with the top. Now this is significant. This is basically saying that if these 64 nodes were generals, and this top node